Hello everybody and welcome to the second part of Lecture 2, Complementary Equations when Bad Things Happen. And here we're going to be talking about the case where the auxiliary equation has either imaginary roots or complex roots. And to help us get an intuitive feel for this, let's take a look at an equation that we've seen before. Here's the complementary equation y double prime plus y equals 0. And I claim that y equals sine of x is a solution. And to show that it's a solution, we'll compute y double prime. And we'll plug y double prime and y into this equation and get 0. So we take y double prime plus y, where y is sine of x, and we get 0. And let me just document this a little bit more fully so that we'll know exactly what just happened. When we take y equals sine of x, then y double prime plus y equals 0. So y equals sine of x is a solution. This is a second order differential equation. So we expect two independent solutions. And you'll never in a million years guess what the other solution is. Well, okay, maybe you will. If sine of x is a solution, it may not shock us that cosine of x is a solution also. And to prove this, we'll compute y prime and y double prime. And we take y double prime, negative cosine of x, plus y cosine of x, and sure enough, we get 0. So if y equals cosine of x, y double prime plus y does indeed equal 0. Now here's what we have so far. Two solutions to the equation y double prime plus y equals 0. Are they independent? If we only have two functions, then they're going to be independent if one of these is not a constant multiple of the other. And I think it's intuitively obvious that there's no constant that we can multiply cosine of x by to get sine of x. So these two things are two independent solutions. And our general complementary solution is the set of all possible linear combinations of these two. So we have the general complementary solution of the equation y double prime plus y equals 0. Now, all of this I did to set up what I'm about to do next. Son of a gun. This is exactly the same equation that we've been working with. But when we did this before, I said, hey, sine of x is a solution, I'll prove it to you. And I did. And then I said, you know what? Cosine of x is also a solution, I'll prove it to you. And I did. And so that meant, since they were independent solutions, that the general complementary solution was the set of all possible linear combinations of sine and cosine of x. Now I'm going to do this same exercise again, but without the foreknowledge that sine and cosine are independent solutions. I'm going to find the complementary solution of this equation using the differential operator method and getting the auxiliary equation and finding the roots to the auxiliary equation and so forth. So I take my complementary equation and write it in terms of differential operators. Second derivative of y plus y equals 0. And then I factor out y. And what I have here is my polynomial phi evaluated at the differential operator t. My auxiliary equation is the same polynomial evaluated at m and set to 0. So here's my polynomial phi of m. And the next thing I have to do is solve this equation phi of m equals 0. Before I shoot myself in the foot, let me correct something. m squared is -1, so m is plus or minus the square root of -1, which is plus or minus I, where I is square root of -1. Heavens to Murgatroyd, we have imaginary roots. Now, before I write down what my independent solutions are, let me give each of these roots a name. I have two distinct roots. I ought to get two independent solutions. Okay, there's my general complementary solution. Holy moly, what on earth do I do with that? Well, we already had a complementary solution to this. We already had a complementary solution to this. And that complementary solution was a linear combination of sines and cosines. The general complementary solution to that equation is also given by the set of all linear combinations of cosine of x and sine of x. Now, in setting these things equal, am I insinuating that e to the ix and cosine of x are the same, and that e to the negative ix and sine of x are the same? I'm not. I'm just saying that the general complementary solution is the set of all linear combinations of e to the ix and e to the negative ix, which is the same as the set of all linear combinations of cosine of x and sine of x. I'm not saying that e to the ix and cosine of x are the same. And I'm not saying that e to the negative ix and sine of x are the same. So perhaps I had better be more careful here and say this. Instead of C1, I'll say A, where A is some constant. And I'll say B sine of x, where B is some constant. So I am saying that these two things are the same, but the coefficient of e to the ix is not going to be the coefficient of cosine x. I'm just saying that any linear combination of e to the ix and e to the negative ix is equal to some linear combination of sine of x and cosine of x. And when we take the course complex analysis, we'll get to see exactly why this is true. Some incentive to take complex analysis when it's offered. Now, can I find out what A and B are here? You know, I think I can. I have to be a little bit sneaky in order to do this, but I think I can. So let's say I have v of x equals c1 e to the ix plus c2 e to the negative ix, and that's equal to a cosine of x plus b sine of x. Now, let me compute the derivative of each of these things. Okay? V prime of x. This is equal to c1I e to the ix minus c2I e to the negative ix. Okay? And derivative of cosine is negative sine, so I have negative a sine of x plus b cosine of x. Now, what on earth did that accomplish? Well, as far as we can tell right now, nothing. But let me do this. Let me plug in some very strategically selected values of x. For example, x equals 0. I'll plug x equals 0 into the complementary solution V. And that's going to make this exponent 0. That's going to make that exponent 0. So we'll have e to the 0, which is 1, e to the 0, which is 1. This just gives us c1 plus c2. Cool. Oh, and if I plug in 0 for x here, I have cosine of x, which is cosine of 0, which is 1, and sine of 0, which is 0. So if I plug 0 in for x into the complementary solution, I get a times 1, or just a. I think I just found out what a is in terms of c1 and c2. Now, how do I find b? Let's take the derivative of the complementary solution and plug in 0 again. If I plug in 0 for x, I have e to the 0, which is 1, e to the 0, which is 1. So I get c1i minus c2i, and I'll factor the I out. Okay. So this is c1i minus c2i. Yep. Now I'll plug in 0 over here. Plug in 0 to sine of x, I get 0. Plug 0 into cosine of x, I get 1. So when I plug in 0 here, I get b times 1, which is just b. Son of a gun. Okay, so this is pretty much how we relate e to the ix and cosine and sine. Whoops, 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 whoops. A cosine of x plus b sine of x. Okay. And we found out that a equals c1 plus c2, and b equals I times c1 minus c2. Okay. So they are not the sine and cosine. Cosine of x is not equal to e to the ix. And sine x is not equal to e to the negative ix. But cosine and sine, the linear combination of cosine and sine, are a linear combination of e to the ix and e to the negative ix. Now, why am I telling you all of this? Why am I telling you all of this? I sure wish I knew. No, I do know. Did I actually manage to squeeze all of that in? I did. Okay. When our process for finding the complementary equation yields a solution of this form, we're going to write c1 e to the imx, c2 e to the negative imx as this: a cosine of mx plus b sine of mx where AB may be complex coefficients. We'll let the applications dictate what A and B turn out to be. Now, if you're thinking deeply about this, and you may, I think deeply occasionally myself, not often, but sometimes I do. You might be saying to yourself, well, okay, these two real constants are the same. What happens when they're not? Where these two things are different. Now, what happens when we have a situation like that? How can I be certain? How can I be certain? Here's why. We're working with linear differential equations with constant coefficients. This will always yield an auxiliary equation with real coefficients. Okay, so far so good, but that doesn't really answer the question yet. Now that's going to take some explaining. Not much, but some. If we start with a differential equation in which the polynomial has real coefficients, then the roots of the equation are either real or they're complex roots that occur in conjugate pairs. Now, what's a conjugate pair? If you had me for Cal 1, you'll probably know. If you didn't, you probably won't, but I'm about to tell you. So A and B are real numbers. We have a complex number. Real number A plus real number B times I. So if we have a complex number, how do we get its conjugate? Just change the sign in between. So if we have the complex number A minus BI and we want to find the conjugate, just change the sign in between and we get the complex conjugate. Now let me make sure we get the point. Crud. no. Here's what I want. Here's what I want. Okay, I finally got it right. I guess the real point here is if you give me enough tries, I'll get it right eventually. But any auxiliary equation that yields this as a root, ki or I times k, that same auxiliary equation will also yield its conjugate, negative ki or negative ik. And we haven't seen this yet, but let me just prepare you for it in advance. Come on, Pat, pick a number, a letter. J plus ik. And to really drive home the point, let me use my red magic marker. You know, I love using it anyway. When we get these complex conjugates, the coefficient of I is essentially the same, other than the plus or minus sign. So if ik is a solution to the auxiliary equation, then negative ik, the same real constant, negative ik is also a solution. If we have m1 equals the complex number j plus ik as a solution to the auxiliary equation, then the conjugate of this thing, m2 equals j minus ik, will also be a solution. But the coefficient of I is the same, other than the plus or minus sign. It's the same number, k. Whenever we're dealing with equations with real coefficients, polynomial equations with real coefficients, this is always the case. The roots appear in complex conjugate pairs. If you have one conjugate root as a solution, if you have one complex root as a solution, you're automatically going to get the other complex root, the conjugate, as a solution as well. So what happens if we have this? Whoops, make that positive. E to the imx and e to the negative I kx, where these things are different. what happens? What do we do when that happens? Nothing. It's not going to happen, so we don't have to worry about it. Oh, but what if it does? It's not going to happen. If we have a linear differential equation with constant coefficients, where the constants are real numbers, this cannot happen. So we don't have to worry about it. Now, let's do some examples. Let's do some examples. We want to find the general complementary solution to this thing. So the first thing we do is rewrite this in operator notation. Second derivative of y plus 4y equals 0. The next thing we do, factor out the y. No, I factored out the d squared. I'm sorry, everybody, I'm on autopilot. Factor out the y. There, that looks much better. And that yields the polynomial phi, evaluated at the differential operator d. From this, we get the auxiliary equation. And here's our polynomial phi of m. To find the complementary solution, the next thing that we have to do is solve that equation for m. Whoops, whoops, whoops. See that? Conjugate pair, 2i, negative 2i. So here's our complementary solution. C1 e to the m1x plus C2 e to the m2x so C1 e to the what? 2. Let's say I times 2x plus C2 e to the negative I times 2x the constants too are significant. This tells us we're going to get a cosine of 2x plus b sine of 2x. And in case there's any doubt at all, this is where that 2 came from. Voila, there's our solution. Now that wasn't so hard. Let me make it a little bit trickier. And it's good that I make it a little bit trickier because your homework assignments are going to be tricky. So let's do the tricky stuff right out in the open here where we can all see what problems may come up and we can all see how to deal with these problems before we're on our own. Here's the complementary equation that corresponds to some linear differential equation with constant coefficients. Can I factor that? I don't think so. I'll get my equation written in operator form, second derivative of y, plus 8 times the first derivative of y, plus 17y. I've written it in operator form. Now I'm going to factor out the y's. Here's our polynomial phi of d, and that's going to give us the auxiliary equation, m squared plus 8m plus 17 equals 0. And again, I look at that and I say, I can't factor that. If I can, I don't know how. So how do I find the solutions? Let's not forget our old friend, the quadratic formula. That's not our enemy, that's our friend. In equations like this, where we don't stand a snowball's chance and you know where of solving it, the quadratic equation comes through, or the quadratic formula comes through like a knight in shining armor to help us solve this. So x equals negative b plus or minus the square root of b squared minus 4ac over 2a. Yikes, I remember it. Okay. Negative b plus or minus the square root of b squared minus 4. A is 1. C is 17. Yikes. All over 2a, where a is 1. Four times 17, that's 68, isn't it? I think it is. Let's see, 40 plus 28, yep. Okay. And I don't know why I used x, force of habit, I guess. Let's see, is that showing up? Yep, I guess it is. So those are our two roots. We get v of x equals c1 e to the m1x plus c2 e to the m2x. Holy stinking moly. Ugh. So that is c1 e to the negative 4 plus I x plus c2 e to the negative 4 minus I x okay. Not knowing what else to do, I'm just going to distribute the x inside the parentheses here. I'm just stalling for time. c1 e to the negative 4x plus ix. C2 e to the negative 4x minus ix. Oh, by the way, notice that the roots of our equation, our auxiliary equation, did come in conjugate pairs. Negative 4 plus I, negative 4 minus I. See, it's always going to work out that way. Now, what do I do with this? Well, I've been studying my formulas because up until a few weeks ago, we were having quizzes in differential equations every Friday. And one of my formulas was, maybe it was this, e to the x, e to the y equals e to the x plus y. Well, you know what? It's an equation. And equations are two-way streets. They go this way, e to the xy equals e to the x plus y. They also go the other way. E to the x plus y equals e to the x times e to the y. Well, this is essentially what I have here. I have e to the power of one thing plus another, or e to the power of one thing minus another. I can split that up into two exponentials, the product of two exponentials. So e to the 4x plus ix, e to the negative 4x plus ix, I can write that as e to the negative 4x times e to the ix. And this thing, e to the negative 4x minus ix, I can split this up into the product of two exponentials, e to the negative 4x times e to the negative ix. Now, I think that's going to help. Oh, I sure hope it does. It will. It'll help. I have a common factor here. E to the negative 4x is a factor of both terms. I'm going to factor it out. E to the negative 4x times C1 e to the ix plus C2 e to the negative ix. Oh, now we just have e to imaginary powers, ix and minus ix. We know how to deal with this. This is going to be a cosine of 1x plus b sine of 1x, and I won't write the 1. Yeah, what's the real number coefficient of x in each case? It's just 1. So we get cosine of 1x, sine of 1x. You know what? I think I'm done. I think I'm done. Let me just rewrite this. That, ladies and gentlemen, is our solution. That's what it looks like. Now, this was kind of tricky, but the good news is it doesn't get any more complicated than this. In all of our complementary equations and complementary solutions, this is as tricky as it's going to this is as tricky as it's going to get. And don't forget our old friend that we used a little while ago, the quadratic formula. It's one of those things that we learned to hate when we were in high school, but it's not something to hate. It's like a good friend that's there when we really need some help. And on this exercise, unless we're psychic, there's no other way that we could have found the roots M1 and M2. We had to use the quadratic formula. And like the knight in shining armor that it is, it came through for us when we needed it the most. Now, I don't think you people are naive. I don't think you are. But certainly you know that I wouldn't give you this instruction without homework. So on page 80, the A exercises 1 and 2, do those. And again, work hard. I'm assuming that you probably have a lot of free time now since we don't really have classes per se. Work hard, get plenty of rest, seriously. At least 8 hours, eat sensibly, and don't expose yourselves to any unnecessary risks. Stay healthy, conduct yourselves judiciously and prudently, and I am eagerly looking forward to when we can see each other again face to face. So please, exercise good sense in all that you do, and one of these days we're going to make it back to the classroom and it's going to be like old times and we'll do just great. Until that time, please work diligently at this. We want to make sure that we get the most out of this semester, and we can. If we work hard at home, we will get just as much out of it as we are if we go to class. So please work hard, and oh, by the way, enjoy your studies. And I say that with a smile on my face, but also in utmost sincerity. Work hard, but enjoy the work that you do. In Ecclesiastes, it says, there's nothing better than for a man or a woman to see good for all their hard work. So work hard and enjoy the fruits of your labors. Goodbye.